This page discusses a really fundamental concept in how processors interact with memory: data alignment. Think of memory as a series of numbered boxes, where each box holds 1 byte. If you have a piece of data that's 4 bytes long, like a standard integer, the most efficient way for the processor to grab it is if it starts at an address that's a multiple of 4, say address 0 for 8, and so on. This is called an aligned access. An unaligned access would be trying to grab that same 4-byte integer starting from address 1. Now, with ARMv6 and v7 architectures, there's some flexibility. They actually allow for unaligned data accesses, which can make programming a bit easier sometimes. However, this comes with a few important conditions. First, not all instructions support this. Only a specific subset of load and store instructions are designed to handle unaligned addresses. Second, and this is crucial, you can only perform unaligned accesses on memory that has been designated as normal memory type, which we saw a few pages back. You can't do this with memory mapped to peripherals, for instance. So, how does the processor handle an unaligned access? It's clever. The load/store unit doesn't magically pull unaligned data from memory. Instead, it performs multiple aligned accesses to fetch the chunks of memory that contain your data, and then it internally shifts and combines them to give the CPU the single piece of data it asked for. While this is convenient, it often means an unaligned access can be slower than an aligned one because it requires more work behind the scenes. While data access has this flexibility, instruction fetching is much stricter. The instructions themselves, the code the CPU executes, must be properly aligned. A standard 32-bit ARM instruction must be word-aligned, meaning its address has to be a multiple of 4. A 16-bit thumb or thumb-E instruction needs to be half-word aligned, so its address must be a multiple of 2. And Java bytecodes, being just 1 byte, are simply byte-aligned, which means they can be located at any address. Finally, the page briefly introduces the concept of Endianness. ARM processors are natively little-endian. This refers to the order in which bytes are stored in memory for a multi-byte number. We'll explore this in more detail on the next page, but the important point here is that ARM processors are flexible. Even though their native format is little-endian, they can be configured to work with big-endian memory systems, which is essential for compatibility with a wide range of devices and network protocols. This page introduces a fundamental concept in computer architecture called Endianness. It's all about the order in which a processor stores bytes of data in memory. Think about it this way: an ARM register holds a 32-bit value, which is 4 bytes. But the computer's memory is addressed 1 byte at a time. So, if you have a 4-byte number, in what orders do you place those 4 bytes into 4 consecutive memory locations? That's what Endianness determines. There are 2 main systems, which are explained in the blue box. First, there's the little-endian system. In this system, the least significant byte, the little end of the number, is stored at the lowest memory address. Let's take a 4-byte number, for example, hexadecimal 0x12345678. The least significant byte is 0x78. If we were to store this number starting at memory address 100, a little-endian system would put 0x78 at address 100, 0x56 at address 101, 0x34 at address 102, and finally, the most significant byte, 0x12, at address 103. The other system is big-endian. This is often more intuitive for us because it's similar to how we write numbers. The most significant byte, the big end of the number, is stored at the lowest memory address. Using our same example of 0x12345678, a big-endian system would store 0x12 at address 100, 0x34 at address 101, 0x56 at address 102, and the least significant byte, 0x78, at address 103. So, why does this matter? Most ARM processors are natively Little Endian. However, the architecture is flexible. As the slide says, they can be configured to access Big Endian memory systems. This is very important for compatibility, especially in networking. The standard for data sent over networks, often called network byte order, is Big Endian. So, for an ARM device to communicate correctly over a network, it needs to be able to handle Big Endian data. Finally, the slide mentions that ARM supports 3 models of Endianness. LE is simply Little Endian, the default. B8, or Byte Invariant Big Endian, is the modern standard for Big Endian support, which was introduced in Architecture v6. And you see B32, or Word Invariant Big Endian, which has been dropped in Architecture v7. This is just a historical note, showing that the way ARM handled Big Endian data has evolved to the more standard B8 model. So, the key takeaway here is understanding the difference between storing the little end or the big end first, and knowing that while ARM is typically Little Endian, it has the flexibility to work with Big Endian systems when needed.